Welcome to the today class of nonlinear vibration. So, today the last class in this NPTEL course, and in this class we are going to discuss about nonlinear vibration of parametrically excited system with internal resonance. So, we will take one example to study how this parametrically excited system with internal resonance behave, and already we have or we will study in this class how to derive this governing equation motion of a base excited cantilever beam with arbitrary mass, which will behave as a system with internal resonance. Then how to solve this equation and how to determine the steady state response, and also we will discuss about different phenomena observed in this type of system. So, already we know a system is said to be internally resonates when frequencies, that is the modal frequencies, let the modal frequencies omega m, if omega m can be written as n omega r. So, where m and r are the modal frequencies, for example, m equal to 2, r equal to 1, and let me take n equal to 1. So, in this case omega 2 equal to omega 1. So, this is known as 1:1 internal resonance. Similarly, if omega 2 equal to 3 times omega 1, so this is known as 1:3 internal resonance. So, if we can take, let us take this way. So, omega 3 is to omega 2 is to omega 1. So, let they are in the ratio of 3 is to, so they can be of the ratio of 3 is to 2 is to 1, or they may be of the ratio, we can take 5 is to 3 is to 1. So, or it can be of 9 is to 3 is to 1. So, we can have different integer relationship between these modes. So, when we will have this integer relationship between these modes, so due to this nonlinear effect, due to these nonlinear terms present in the equation motion, so one can show that the higher modes are resonated when the system is excited at a frequency near to the lower mode frequency. So, in that case, as the higher modes are excited by these lower modes, or the lower modes are excited by the higher modes without any external force. So, that is why the system is said to be resonates internally, or in other words one can tell this internal resonance occur in a system when there is, when the modal frequencies are commensurate. So, in this case one can have this 1:1 internal resonance, 1:2, 1:3, or 3, one can tell this as 1:2:3 or 3:2:1 depending on the frequency relation. So, today class we will study a system which already we know a parametrically excited system. We can take a cantilever beam. So, let this is the cantilever beam, and the base of this cantilever beam is excited, it is moving up and down. So, with periodic force Z equal to Z0 cos omega t. So, already we have discussed this system, or we know that for some value of this Z0 and omega, the system will start buckling, or the system will try to vibrate in a transverse direction. So, the system will try to vibrate in a transverse direction, or it will come out of its trivial state. So, this is the trivial state and this state is the non-trivial state. So, this is the non-trivial state. So, non-trivial state and this is the trivial state. So, either one can apply this base excitation Z equal to Z cos omega t, or one may apply periodic axial load. So, if one apply periodic axial load also, so the system may be that of a parametrically excited system. So, if a periodic axial load P0 plus P1 cos omega t is applied to the system. So, for some value of P1 and omega and P0, the system start buckling. So, we know that in case of static loading, so if it is greater than the critical Euler buckling load, then the system start buckle. But in case of dynamic loading, so if this value, this amplitude is very less than this critical Euler buckling load also, so the system starts buckle for some value of P1 and omega. So, today class will study or will see a system where it is base excited, and if we put a mass at arbitrary position by changing this value or by changing this position of this mass, we can show that for some system parameter or for some position of the system, the natural frequencies of the systems are commensurate. That means, we can show, we will take a frequency relation omega 2 is to omega 1. So, which is nearly equal to 3 is to 1, and taking cubic nonlinearity in the system will show how the system response becomes. So, let us take the system, let us consider this is the system. This system has been considered by many authors. For example, this system is considered by Zavodini and Nafe. And many papers on these have been studied by Dwivedi and Kaur. So, from 1999 to 2003, 9 publications are on the system, and Zavodini and Nafe, they have considered the system in 1989. So, in their system they have considered a base excited system Z t equal to Z0 cos omega t, and they have taken only single mode approximation. But as we are interested to study the internal resonance case, by varying the mass position, one can show that the system has many different type of resonance condition. For example, one can have this internal resonance condition of 1:3, 1:3:5 and 1:3:9. So, this is 2 mode interaction and these two are 3 mode interaction. So, one can study. So, let us study in detail about this 2 mode interaction of the system, and for 3 mode interaction. So, some reference papers will be shown and one can refer this paper to study or know more about this 3 mode interaction. So, let us first derive this equation motion. So, now let us consider due to this vibration. So, let it has take a small element. So, in this small element one can write what are the forces acting. The forces, this is the inertia force rho v double dot zeta t, then this is the inertia force in x direction. So, this is the weight rho g, and this is the inertia force in y direction rho u double dot zeta t. So, we have taken this transverse deflection to be v and this axial direction deflection to be u. So, in x direction it is rho u double dot and in y direction it is rho v double dot. So, these are the inertia force, and damping force, including the damping force, this is C v dot. So, if the mass is taken into account, so this is the end mass. So, end mass also will have this m u double dot m v double dot. So, this is the position at a distance d from this base. So, this is the deformed length d, this is undeformed length L, L is the total length of the beam considering inextensibility condition. So, now we can find the equation motion. So, we have taken a small element at a distance zeta and we are finding the equation motion of the system with respect to the space coordinate s and time t. So, here v is the y direction deflection and u is the deflection in the longitudinal direction. So, one can use the basic equation of the strength of material to derive the equation motion. So, we know this bending moment of the system can be written in this form. this is equal to E I by R. So, which is equal to also E I del phi by del S. So, where this phi dash can be written as d of that function by del of that function by del S. R is the radius of curvature. So, the slope tan phi. So, slope this angle is phi. So, the slope tan phi can be written in this form d phi by del S, and from this figure we can know the sin phi. So, we can write the sin phi in terms of this. So, sin phi equal to del V by del S. So, we have taken del V. So, this is V. So, for a small displacement del V. So, del V by del S will be sin phi. So, this is equal to V dash. So, if you differentiate this sin phi, so we can write this cos phi equal to, so cos phi del phi by del S equal to V double dash. So, now from tan phi equal to del phi by del S. So, we can write or we can get this del phi by del S equal to V double dash by root over 1 minus sin square phi, or we can write this del phi by del S equal to V double dash by root over 1 by substituting the sin phi equal to V dash, that is del V by del S. So, we can write this V double dash by root over 1 minus V dash square. So, this can be written as V double dash by taking this or taking this part to the numerator. So, we can write this is equal to V double dash into 1 minus V dash square to the power minus half, or this is equal to V double dash into expanding this thing binomially and taking the first term only. So, we can write this equal to V dash into 1 plus half V dash square. So, now we can substitute this del phi by del S in this equation ms. So, this del phi by del S we can write in terms of, so ms we can write equal to E I del phi by del S equal to E I V double dash plus half V dash square. So, in this way the nonlinearity is introduced in the system. Otherwise, if you take the simple Euler-Bernoulli beam equation, the equation will becomes this ms, that is the bending moment can be written as E I del square V by del y x square, but in this case as we have taken this nonlinear term. So, we have one additional term here in this equation. So, ms equal to, so ms, so we can write this ms equal to E I V double dash into 1 plus half V dash square. So, here we have introduced this nonlinear term. So, in case of linear term already we know this is equal to E I V double dash. So, now we can write this, the moment of the beam can be expressed as the sum of 3 moments. One is m1 plus m2 plus m3. So, where m1 is the external moment at S due to longitudinal inertia of the beam element d zeta and mass m. m2 is the external moment at S due to lateral inertia. So, longitudinal inertia we can take, that is mu double dot, lateral inertia mv double dot. Similarly, external moment at S caused by angular acceleration of the mass m, that is the attached mass we are putting due to this mass moment of and due to mass moment of inertia j. So, taking all these thing into account. So, our m1 equal to minus S2 integral S to L. So, rho V double dot. So, we have added the damping also, and we have used this Dirac delta function to write the position of the tip mass at a distance d from the base. So, rho is the mass per unit length of the system. So, we can write the equation motion, or we can write this m1 due to lateral moment. So, this into integral S to zeta cos phi d zeta. So, as we are finding, so we have to find the component of, so we are this force into, so this is the force. So, as we are taking the moment about point S, so we have this force. So, mu double dot. So, this is the force and into this distance. So, this distance for this small d zeta. So, we can find that component along this direction, and in that way. So, we can find this m1. Similarly, we can find m2. So, while finding m2, so we have this u double dot minus g, along with that. So, u double dot minus g, and also we should take this mass into account using this Dirac delta function, and we have this m3 due to that rotary inertia j delta. So, as we are attaching this mass, so we are using this Dirac delta function here, and one can use this inextensibility condition u zeta t equal to zeta minus 0 to zeta cos phi. So, as the length is not changing, so this is ds, this is dx, and we can taking this inextensibility condition. So, we can write this equation. So, we can relate this u with respect to this v of the system. So, differentiating it twice. So, we can write this u double dot in this way. So, now introducing this. So, we can write the governing equation motion using Hamilton using this differentiating this equation twice. Now, substituting this expression for m1, m2, m3 in this equation and differentiating this equation twice. As we are differentiating bending moment twice, we will get the loading equation or the force equation. So, we have this equation motion. We obtain the equation motion which is written in the space and time coordinates. So, v is a function of space and time. So, in this equation contain this del fourth v by del s fourth. So, this is the linear term present in the Euler-Bernoulli beam equation, and one can note these are the additional nonlinear terms present due to the term what we have considered in our equation in the bending equation. So, differentiating that bending equation twice, we obtain this equation. So, these are the additional nonlinear terms. So, all these terms are nonlinear terms present. So, this is also another nonlinear terms. So, present in this equation. So, this is subjected to boundary condition. So, at base at s equal to 0, the displacement and slope are 0, and also at the end. So, we have the shear force. This is shear force proportional to shear force and this proportional to bending moment. So, shear force and bending moment are 0 as we are not putting the mass at the tip. So, the mass is put at some arbitrary position, that is why at the tip. So, at s equal to L. So, we have this bending moment which is proportional to V s s and shear force which is proportional to del q V by del s q equal to 0. So, now we can assume a solution in this form V s t equal to n equal to 1 to infinity. So, we can take number of modes, we can limit our number of modes instead of taking infinity, we can take up to 2 mode or 3 modes depending on the modal interaction. So, if we are considering only 2 mode interaction, so we can take this term instead of taking infinity. So, let me write this n equal to 1 to n. So, this n can be infinity if we are taking infinite number of terms, or it can be finite if you are taking a finite number of terms. So, this depends on the modal participation we are taking in this case. So, here r is a scaling parameter. So, psi n. So, the psi n is the shape function, n is shape function, and u n is the time modulation. So, we can applying this extended Galerkin method, we can reduce or we can minimize the residue as the function what you are taking is not the exact function of the system. So, we can, so there will be some residue in the system. So, that residue can be minimized by using this generalized Galerkin method by using this equation. So, that is r is the residue. So, r into psi n into dx, we can integrate it from 0 to L and equate it equal to 0. And let us take these are the non-dimensional parameter, x equal to s by L, beta equal to d by L. So, this is the position parameter, and this tau non-dimensional time. So, we can take it equal to theta 1 into t, where theta 1 is the fast mode frequency, and omega n equal to so non-dimensional natural frequency can be written as theta n by theta 1. Lambda equal to, this is the scaling parameter, non-dimensional scaling parameter, mu is the mass ratio, mu equal to m by rho L. So, this non-dimensional forcing amplitude equal to Z0 by ZR. Similarly, J equal to J0 by rho L R square, and external frequency phi equal to non-dimensional external frequency phi equal to omega by theta 1, where this theta 1 and other terms. So, after writing this thing, so we can, after applying Galerkin method, so this equation reduced to this form. So, this equation can be written as un double dot. So, this is written in terms of the time modulation. So, it is equal to un double dot plus 2 epsilon zeta n un dot plus omega n square un minus epsilon. Epsilon is the bookkeeping parameter, m equal to 1 to infinity f n m u m cos phi tau. So, this is the, so one can note here that this time varying, so this time varying term, that is f n m cos phi. So, this time varying term f n m cos phi tau is the coefficient of u m, as this is coefficient, or as this parameter is coefficient of the u m, that is the response of the system. That is why this is known as parametric forcing term, and in addition to that we can see the systems contain all these nonlinear terms. So, this nonlinear term where this is the product of 3 displacement term u k, u l and u m, and this contains u k, u l dot and u m dot, and here also it contains u k, u l and u m double dot. So, the first one, that is product of u k, u l, u m. So, if k equal to l equal to m, so this becomes u cube. So, this is a geometric nonlinear term, cubic geometric nonlinear term, and these two, so where this u k, u l dot and u m dot. So, product of two velocity term gives rise to inertia term. That is why this term is known as inertial nonlinearity term. So, this is also cubic inertial term, and this also where this inertia u m double dot is the acceleration term, it is multiplied with this displacement term, and as due to presence of acceleration term. So, this is also known as cubic inertia nonlinearity. So, in the system, in addition to this parametric forcing term, so we have cubic geometric and inertia nonlinear terms. So, now, so this equation is written in terms of the nth mode, and one can note that this forcing function m equal to 1 to infinity contains the interaction of the other modal frequencies, other modes also, because one can take, instead of taking n, so one can have this interaction of the other modes. So, this term can be taken from this u m term. So, u m, so it can be u 1, u 2, u 3, that means the nth mode is influenced by the presence of the other mode in the system. Similarly, in this nonlinear terms also we have the summation k equal to 1 to infinity, l equal to 1 to infinity and m equal to 1 to infinity. So, that means the nth mode is so nth mode is influenced by the other k, l and m mode present in the system. So, we can take, so here the coefficient of those terms, coefficient of this equation can be seen from this. So, where theta n square is the actual nonlinear frequency of the system. So, this is written in this by this expression. Similarly, this forcing amplitude of the forcing function can be written by this expression. So, this frequency term contain the term with Young's modulus I, and then this k n term, k n is the k n fourth. So, this is the characteristic. So, this has come from the characteristic equation, and rho mass per unit length, and this is the scaling parameter. So, also this contain this these terms, that is S31, these are the integral terms, mu is the mass ratio, and these are the integral terms present in the system. So, this is the forcing term. So, forcing term contains this frequency of the forcing, amplitude of the forcing, then this fast mode frequency, then these are the integral term H33 and H34 are the integral term. So, which are defined after this slide. So, this is the nonlinear term alpha n k l m, and this is beta k l m and gamma k l m. Beta and gamma are nonlinear inertia term, and this is the coefficient of linear, this is the coefficient of cubic geometric nonlinearity. So, these are the expression for the integral what we have used in this equation. So, one can see, so there are many integral terms one has to evaluate for finding the coefficient of the system, where this psi n is the shape function of the system, and in this case the shape function is taken that of a cantilever beam with tip mass. So, one can take, or cantilever beam, one can take the shape function of a cantilever beam also, which satisfy the geometric boundary condition. That means, it satisfy the geometric boundary condition here at the left end, that is displacement and slope equal to 0, or one can take the shape function of a cantilever beam with arbitrary mass position. So, by taking these, so one can find all these integrals. So, one can note that in some places one can find only single integral, and other places one can find double and triple integrals also in the system. So, one should be very careful. So, here one can have triple integral terms. So, here double integral terms are present. So, twice the system. So, integration has to be performed. So, one has to take care while finding this coefficient of the system. So, after finding this coefficient of system, so one can see, or we have already discussed, that the system can have external resonance conditions. So, in case of the parametrically excited system, when this external frequency equal to summation of other modal frequency. For example, so if omega equal to omega m plus minus omega n, so we can have resonance condition. So, in this case this m and n are modal frequency. If m equal to n, then we can tell this as principal parametric resonance condition, and f not equal to n. So, this is known as combination resonance condition. So, in case of combination resonance condition, we can have some type or we may have different type. So, one can have all these type of resonance condition. So, this principal parametric resonance condition can be of nth mode, or n can be of first or second, third or higher modes. So, in that case it will be principal parametric resonance of first mode, second mode, third mode, or combination resonance of first and second mode. If m equal to 1, n equal to 2, then it is some type combination resonance of first and second mode of some type. Then one may have difference type also. So, let us take the condition when we are considering this principal parametric resonance of first mode. That means, omega is nearly equal to 2 omega 1. So, we will consider the case in the neighborhood of twice omega 1. So, to take into account the nearness of omega, that is the external frequency, to twice the natural frequency, we can take a detuning parameter epsilon sigma 1. Sigma 1 is the detuning parameter. So, and as we are discussing about this 1:3 internal resonance case. So, as we are considering internal resonance case of 1:3, so we can take this omega 2 nearly equal to 3 times omega 1, and this is the detuning parameter which will take care the nearness of this omega 2, that is the second mode, to that of 3 times omega 1. So, here we are taking this epsilon as the bookkeeping parameter, and we already know this bookkeeping parameter should be very less than 1. So, now let us use this method of multiple scale to derive the resulting equation or reduced equation, which we can further use for finding the response and stability of the system. So, using this method of multiple scale, so we can write or we can reduce the temporal equation, and for that purpose let us take this un equal to, that is the time modulation un equal to un 0 plus epsilon un 1. So, un0 and un1 are function of time, different time scales, that is t0, t1. So, if you take up to t1 only of the order of epsilon. So, here we are taking this Tn equal to, already we have discussed this. So, Tn equal to epsilon Nt. So, where as we are taking this non-dimensional time tau, so we can put this equal to epsilon to the power n into tau. So, our T0 n equal to 0. So, this is equal to tau and epsilon equal to 1, T1 equal to epsilon tau. So, where we are taking this n equal to 1 to infinity. So, by substituting this equation in the temporal equation, so we can, and separating the terms in the order of epsilon 0 and epsilon to the power 1. So, we have these two equations. So, the first equation is this, which can be written as d0 square un 0 plus omega n square un 0 equal to 0. So, in that case we know the solution of this equation, or we can write the solution of this equation in the form a n t 1 e to the power I omega n t 0 plus its complex conjugate, and substituting this equation in the second equation, that is d 0 square u n 1 plus omega n square u n 1 equal to minus 2 zeta n d 0 u n 0 plus 2 d 1 d 0 d 1 u n 0 minus n m equal summation n m equal to 1 to infinity f n m u m 0 cos phi tau plus. So, these are the nonlinear terms. So, substituting that u term here in this equation. So, we can have some terms which are known as secular or mixed secular or near secular terms. So, as we know that these terms will lead to infinite response and the system has a definite response. So, we have to eliminate these secular terms. Now, eliminating these secular terms. So, for n equal to 1, so we can write this equation. So, in this equation for n equal to 1, we can write this is equal to 2 I omega 1 into zeta 1 a 1 plus a 1 dash minus half f 1 1 a 1 bar e to the power I epsilon sigma 1 t 0 plus f 1 2 a 2 e to the power I epsilon sigma 2 minus sigma 1 t 0 plus n equal to or j equal to 1 to infinity, j equal to 1 to infinity. So, this is a equivalent term alpha I 1 j a j into a j bar into a 1 plus q 1 to a 2 into a 1 bar square e to the power I epsilon sigma 2 t 0 equal to 0. Similarly, as we are taking only two mode interaction, we can expand up to n equal to 2. So, similarly, for n equal to 2, we can write this term by eliminating the secular term equal to this, that is 2 I omega 2 into zeta 2 a 2 plus a 2 dash, where a 2 dash equal to d a 2 by d t 1 minus half f 2 1 a 1 e to the power I epsilon sigma 1 minus sigma 2 into t 0 plus j equal to summation j equal to 1 to infinity alpha e to j a j into a j bar into a 2 plus q 2 1 a 1 q e to the power minus I epsilon sigma 2 t 0 equal to 0, and for n greater than 3. So, this equation is written in this form 2 I omega n zeta n a n plus n dash plus j equal to 1 to infinity alpha I n j a j bar into n equal to 0. And one can note from this third equation, that is n greater than equal to 3, as neither forcing or internal resonance cases are there. So, with due to the presence of damping term, so this will, the response amplitude will decay and the system will come back to the original trivial state for n greater than equal to 3. So, we have to consider only the first two cases, that is n equal to 1 and n equal to 2. because for n greater than 3, due to presence of damping and absence of internal and external forcing, the system will decay to the trivial state. So, let us take, so in the previous expression, so these are the terms alpha I equivalent terms. So, alpha E n j equal to alpha n j plus beta n j plus gamma n j, where alpha n j can be written as 3 into alpha n n n n. So, j equal to n j k l m are written in terms of n. Similarly, alpha n j can be written as 2. So, for j equal to n, so it is written in this form, and j not equal to n. So, alpha n j is written equal to 2 into alpha n j j plus alpha n j j n plus alpha n j n j. So, in that way one can write. Similarly, one can write this beta n j for j equal to n, j not equal to n. Similarly, gamma n j. So, this is the expression for gamma n j for j equal to n and j not equal to n. And Q12, which accounts for the internal resonance terms. So, one can write these expressions. So, these are coming due to the nonlinear terms alpha, beta and gamma. So, writing these terms, so already it is been told that as for mode n greater than equal to 3, the modes are neither directly excited by external force or indirectly excited by internal resonance. So, from that equation it can be shown that these modes die out due to the presence of damping. So, now by taking A equal to half A e to the power I beta. So, we can write this equation by separating the real and imaginary parts. So, we can write this equation in this way. So, these are known as the reduced equation. So, in this case we are getting 4 equations. So, these 4 equations are known as the reduced equation. So, these equations can be written. So, this is the first equation 2 omega 1 zeta 1 a 1 plus a 1 dash minus half f 1 1. So, this is the forcing term f 1 1 a 1 sin 2 gamma 1. So, here we have initially we have substitute a equal to half a e to the power I beta. So, after substituting e to the power I beta, so we can, so as the resulting equation will contain this time explicitly, so we can write those equation in its autonomous form by writing or by transforming this beta in terms of gamma. So, we can write this gamma equal to or gamma 1 equal to minus beta 1 plus half sigma 1 T 1 and gamma 2 equal to minus beta 2 plus 1.5 sigma 1 minus sigma 2 T 1. So, in this way by writing this equation in terms of gamma 1 and gamma 2. So, we can write these terms this way. So, now we have reduced this equation to a set of first order equation. So, these reduced equation, so these are the reduced equation we have already written. So, for steady state, as these A and gamma, that is the amplitude and gamma are not function of time. So, we can substitute these terms equal to 0. Hence, one obtain a set of nonlinear algebraic or transcendal equation which are solved to obtain the steady state solution. So, one can obtain the steady state solution A 1, A 2, gamma 1, gamma 2 by solving those transcendal equation. So, A 1 is the first mode amplitude, A 2 is the second mode amplitude, gamma 1 is the first mode phase angle and gamma 2 is the second mode phase angle. So, and to study the stability of the system, to study the stability of the trivial state. So, the steady state trivial state what we obtained are steady state fixed point response. To study the steady state fixed point response which may be trivial or non-trivial. So, one can perturb this equation, but while perturbing this equation due to the presence of the terms like A 2 gamma 2 dash, A 1 gamma 1 dash. So, when we will perturb these terms, so it will contain the term A 1 and A 2. So, the perturbation will not contain the term delta gamma 1 dash and delta gamma 2 dash for the trivial state. As for the trivial state, this A 1 and so A 1 dash and A 2 dash are 0. So, for the trivial state as A 1 and A 2 are 0. So, it will not contain due to the presence of this product term. So, it will not contain these terms. So, one has to transform this into its normalized form. So, by substituting this P I equal to A I cos gamma I and Q I equal to A I sin gamma I, where I equal to 1 to 2. So, by substituting this P I equal to A I cos gamma I and Q I equal to A I sin gamma I. So, these 4 equations are now reduced or retained in its normalized reduced equation in terms of P 1 and P 2. So, we can have a set of equation in terms of P 1 dash, Q 1 dash, P 2 dash and Q 2 dash, P 2 dash and Q 2 dash. So, these are uncoupled. So, uncoupled in terms of A and gamma. So, now one can easily perturb these equation to find the response or stability of the system. So, now by perturbing this equation one can write or one can find the Jacobian matrix. So, Jacobian matrix is JC. So, which is obtained by the first derivative of the terms of that equation. So, one can write or one can find this Jacobian matrix. So, after finding the Jacobian matrix, so one can find the solution, one can find the response by, for the steady state response one can find the response by solving the equations. So, after solving these equation or after getting the response, then one can study its stability, and the first order equation can be written in this form, that is U 1 equal to A 1 cos omega 1 plus epsilon sigma 1 by 2 into tau minus gamma 1, and U 2 equal to A 2 cos omega 2 plus epsilon 1.5 sigma 1 minus sigma 2 tau minus gamma 2. Or these equations can be written in terms of P 1 and P 2 in this form. So, it can be written in terms of P 1 P 2 by P 1 cos omega 1 tau plus Q 1 sin omega 1 bar tau, and U 2 equal to P 2 cos 3 omega 1 bar tau plus Q 2 sin 3 omega 1 bar tau, where this omega 1 bar equal to omega 1 plus half epsilon sigma 1. So, in this way one can find the first order solution, and one can plot the solution to find the response of the principal parametric resonance case. Similarly, one can study the combination resonance. So, in case of combination resonance, if somebody take this external frequency equal to omega 1 plus omega 2 and internal considering internal resonance omega 2 equal to 3 times omega 1. So, one can write this omega 2 equal to 3 omega 1 plus epsilon sigma 2, and this phi, that is external frequency equal to 4 omega 1, omega 1 is 3 times omega 1, omega 2 is 3 times omega 1 plus omega 1. So, this becomes 4 times omega 1. So, phi nearly equal to 4 omega 1 plus epsilon sigma 1. So, this is equal to omega 1 plus omega 2 plus epsilon into sigma 1 minus sigma 2. So, now in that temporal equation, solving the temporal equation in the similar way. So, one can get a set of these 4 equation for the combination resonance in terms of, one can initially write in terms of A and gamma, and following the similar logic in case of the principal parametric resonance, as the trivial state will not contain the terms with perturbation terms. So, one can write the normalized equation. So, one can write this normalized equation in terms of P 1 dash, Q 1 dash, P 2 dash and Q 2 dash. So, these are the normalized equation. So, one can follow this procedure, that is first find the reduced equation, obtain the Jacobian matrix to study the stability, make the term with time derivative equal to 0 and obtain a set of algebraic or transcendental equation. Find the trivial state stability by finding the eigenvalue of the Jacobian matrix, check the bifurcation point. So, these bifurcation point will act as the nucleation of other stable and unstable fixed point, periodic and quasi periodic or chaotic response. So, one has to check these bifurcation points, and for few frequency point, so solve the reduced order equation numerically to obtain the steady state response. So, use the obtained response as initial condition in the Newton's method for solving the set of nonlinear equations obtained by substituting the time derivative terms equal to 0. So, generate more and more initial points to use it in the Newton's method for different frequency conditions. So, with all such conditions, find the multi-valued response point, So, study the stability of these response points using Jacobian matrix, separate the stable and unstable points and plot these points with different color or line points to show the system response. So, let us take one physical example and see how we obtain the response of the system, or how the simple system behave in a nonlinear way. So, in this physical example, we have taken this length equal to 125.4 mm, f equal to, so I equal to 0.048351 mmq, E. So, all these parameters are given here. So, the roots of the characteristic equations are found numerically to be 1.80097. So, these are the first two roots, and 3.2836, and the corresponding non-dimensional natural frequencies are omega 1 equal to 1 and omega 2 equal to 3.33179, as it is nearly equal to omega 2 nearly equal to 3 times omega 1. So, we have taken these as 3:1 internal resonance condition. Here the bookkeeping parameter and scaling factor are taken as 0.001 and 0.1 respectively. The coefficients of these terms are found out, and so these are the coefficients of the terms, and so one can plot these instability regions. So, first when one plot this instability region, one can observe that due to the presence of internal resonance, so here one can observe this king type of phenomena here. So, if one take a line here, so this shows this part is stable, this is unstable and this is stable, but when we consider this internal resonance case, so one can see multiple stable unstable branches. So, up to this the system is stable, then here to here the system is unstable, then again here it is stable, then again here it is unstable, then stable, then unstable, then again it is stable. So, one can have multiple stable and unstable region in the trivial state of the system when we are considering internal resonance in the system. So, from this one can obtain the response curve. Here A1 and A2 are the response curve is plotted. So, A1 is shown in this line with the circle mark, and A1 is the line without circle mark. The solid lines are stable branch and the dotted line are unstable branch. So, one can observe many bifurcation points in the system. For example, here one can observe the supercritical pitchfork bifurcation point, and here one can have the subcritical pitchfork bifurcation point. Similarly, here these points correspond to the saddle node bifurcation point, and this point correspond to this hop bifurcation point. This is also hop bifurcation point. So, as we have several sets of bifurcation points, so these bifurcation points will act as nucleation of other type of response of the system. So, this is the fixed point response of the system is plotted. So, one can have other periodic, quasi periodic and chaotic response of the system. So, to show the alternate, so this part is zoomed. So, by zooming this part one can see the system has alternate stable, unstable, stable, unstable branches in this trivial state. So, this is the forced response. Previous curve we have shown the frequency response. So, frequency response is plotted with respect to this A1, A2 versus this frequency for different system parameter. Here it is plotted with respect to this forcing parameter. So, this is the, so here also one can see several bifurcation points, and here one may note that after this point, as there is no stable state present in the system will fail due to this catastrophic blue sky catastrophe phenomena. And here one can explain the jump up and jump down phenomena in the system. For example, by increasing this gamma from this position, one can see the system will jump from this point to this point. So, this is a jump up phenomena. Similarly, after this, so one can observe that it can jump from this to this branch also. So, there will be lot of jump up and jump down phenomena present in the system, and this response curve is obtained for the combination type of resonance. So, this is one can plot the bifurcation set by plotting different different bifurcation points. So, this is the trivial state bifurcation point. In addition to that, these are the non-trivial state bifurcation point in the system. So, in this way one can plot different fixed point response of the system. Also, by using this reduced equation or by solving this reduced equation, one can see near this half bifurcation point, one can obtain a set of periodic solution. So, by changing the system parameter, one can show that this periodic solution becomes 2 period, and further changing this parameter, one can observe a chaotic response of the system. So, one can plot the Poincare section. So, up to this it is periodic, then 2 periodic, then 4 periodic, and then chaotic response of the system. And one can use this Feigenbaum number to check or to find whether they satisfy this Feigenbaum number or not in case of the period doubling root 2 chaos. So, one can see different type of crises also in the system. For example, in this case one has, this is one of the attractor, and as it is come in contact with a unstable fixed point response, then it explodes, and one can have this interior crisis of the system, because this original attractor is now a part of the bigger attractor or inside this bigger attractor. That is why this is interior crisis in the system. Similarly, one can observe that these two attractor merge to form a single attractor, and that is why this is known as attractor merging crisis. Similarly, one can find, so initially a quasi periodic response, and this torus, by changing the system parameter, one can show this torus breakdown, and finally it forms a chaotic response. So, this is torus breakdown root 2 chaos. Similarly, so this torus breakdown root 2 chaos is shown by using this Poincare section. So, this is periodic, this is quasi periodic response, initial quasi periodic response, this is shown by Poincare section in this closed orbit, and then it break down. So, when it is breaking down, so this discontinuity comes into picture, and finally it becomes chaotic. So, this is the chaotic response of the system. So, some other intermittency root 2 chaos also are observed in this type of system. So, in this case we have seen that due to the presence of internal resonance and external resonance in this parametrically excited system, though the system looks very simple, but it behaves or it shows many complicated phenomena like chaotic response, fixed point response, periodic response, and chaotic response. Different type of crises are also observed in the system. So, in this way one can study different type of systems and study the nonlinear phenomena associated with this. So, one can take some exercise problems also. So, in this exercise problem one can see this is a longitudinally vibrating elastic rod coupled by different springs. So, one can take, so this is the longitudinal vibration. So, one can derive this equation motion of the system, and one can derive the nonlinear equation of motion of the system by taking these springs to be nonlinear, and finally, one can find or one can check some conditions for which both the beams will show some internal resonance, and one can solve this problem to find different nonlinear phenomena associated with the system. So, the basic equations for this system is developed by Erol and Gurgos. So, it is published in the paper Journal of Sound and Vibration in 2004. So, one can solve this or take this as a exercise problem and solve this equation. Similarly, another case, similar system with some tip mass, by this tip mass can be either at the tip or one can put this tip mass at some intermediate position. So, in this case either one can take the system as longitudinally vibrating system or transversely vibrating system. As one takes a double pendulum. So, without complicating the system, by taking only single mode approximation one can have two equations, and by taking these springs to be nonlinear one can derive this equation motion, or by taking this beam to vibrate or taking this large displacement as in the present case. So, one can study the equation with and without internal resonance. So, this paper is also published in Journal of Sound and Vibration in 2001. So, one can take this as a exercise problem and one can find many nonlinear phenomena in this case, though the original papers are on linear systems where only natural frequency of the systems and linear response of the systems have been found. So, the nonlinear phenomena can be obtained by extending these cases. So, for further study, as this is the last class in this course, so for further study one can take or one can study these papers which are published in Journal of Sound and Vibrations. So, these three papers are by this Gurgos and these two papers also are by Gurgos paper, and they are particularly based on this beam with tip mass and without tip mass. Also one can see most of the lecture in this course have been taken from the work or from the book by A.H. Nafe and D.T. Mook on nonlinear oscillations, and one can refer the other books by Nafe, that is Introduction to Perturbation Technology, Perturbation Method, and the book by Stupnica, The Behavior of Nonlinear Vibrating System. So, it has 2 volumes. Then the book by Cartmel, Introduction to Linear, Parametric and Nonlinear Vibrations. So, these books, these are very good books on this course, and in this course material these books have been referred extensively for finding the or for preparing the study material. Also this book has also been used extensively in this course, that is the book by A.S. Nafe and B. Balachandran, Applied Nonlinear Dynamics, and these papers are also been referred in this work for studying the stability. For example, studying the stability of the sandwich beam, this paper has been used, that is K Saito, H Saito and Otomi, the parametric response of a horizontal beam carrying concentrated mass under gravity. So, this paper and this paper also has been referred, H Saito and Koizumi, parametric vibration of horizontal beam with concentrated mass at one end. So, these papers can be referred, and these two papers also by Zavodini and Nafe may be referred, and these are some of the more references for further study in this course. So, one can study these papers, further paper in this course, and these are also some more references given in this work, and these are some of my references or my work in the parametrically excited system, which are published from 99 to 2003 and are part of my PhD thesis, which is submitted to IIT Kharagpur in 1999. So, these paper may also be referred for further study for 3:1:3:5 internal resonance or 1:3:9 internal resonance. Already these textbooks have been shown in the first class. of the course. So, one can refer all these things, and also in addition to that one can refer the journal papers or the journals for further study. For example, one can refer this journal on this International Journal on Nonlinear Mechanics, Nonlinear Dynamics, Journal of Sound and Vibration, Journal of Vibration and Acoustics, Journal of Dynamical Systems Measurement and Control, Physics D, Nonlinear Phenomena, Cao, Soliton and Fractals, International Journal of Nonlinear Science and Numerical Simulation, Journal of Computational and Nonlinear Dynamics. So, in these journals lot of papers are there which based on recent developments. So, for further study one can refer the journals, and one can have many more, or one can study many different phenomena, or one can know many different nonlinear phenomena and nonlinear phenomena associated with different systems. So, this way this course is over with this module of applications of nonlinear systems. I hope you have enjoyed this course. Thank you very much.